Okay, I think I'm recording. Let's give this a shot. So what I want to do today, let's just pretend like today's class. I'm going to keep it pretty short, I think. But what I want to do is I want to clean up a little bit of stuff and start with something new. The thing I want to clean up is I want to talk a little bit more about probability and wave function. So I had said, I think last time we met, or before that maybe, I was talking about the wave function, and this could be that's how we talk about a wave function, or we represent it, psi, psi. And um, the psi squared is really the probability of finding a particle at a particular space and time. And another way to think about it, and maybe this makes it a little bit easier, is if we treat these particles like they are waves, right? So if a particle is a wave, then we can think of psi as the wave amplitude. So really you just look at the amplitude. And that kind of makes sense because if you're going to say that a particle acts like a wave, right, then you must be able to write an equation that looks like a wave equation, right? Remember, in general, wave equations are sort of like A cosine omega t or something like that, right? It doesn't really matter what the formula is, but where A is the amplitude, and this is a sine function. Okay, or something else. So the idea is that if we're going to treat these particles as waves, then this would represent the wave amplitude. If we treat them as particles, then we got to treat them on a probabilistic basis, meaning we got to talk about the probability of finding them. So if a particle acts like a particle, then psi squared is the probability of finding that particle, just like we said before. Okay? We can't even figure out where a single electron goes in space. We just don't know. And that's the whole Heisenberg uncertainty principle. That's the whole idea. Now, I want you to pause this video and go find something for me. What I want you to find is a packet that I gave you, I don't know, mod 3 or 4, and it was practice AP problems. And I want you to find the packet, and it says at the top of them, AP Physics 1, in AP Physics 2 course and exam description. Okay, and I want you to find problem number 21. So go ahead and pause until you find this. Okay, welcome back. I'm assuming that you found it. We are looking at 21. We've done this before, but we're going to look at it again. And the idea, just in the off chance you couldn't find it, is that they graphed wave functions of two particles. This is particle X and this is particle Y. And the idea is this is what we call amplitude on the y-axis, amplitude, and this is its location on the x-axis, so same thing. And the first one sort of is a little bit more spread out. Kind of gets big like that. And pretend it's a little bit more centered on the x-axis. I kind of screwed up a little bit. And this one's a little bit tighter. Again, centered on the x-axis. And it goes a little bit higher. So if we say that A sub 0 is the maximum amplitude for particle X, here's A sub 0 here. Okay, so you can see that in particle Y it goes a little bit higher. The amplitude is higher. And so what it says is the figure above shows graphical representations of the wave functions of two particles, X and Y. Okay, I just drew those. And they are moving in the positive X direction. The maximum amplitude of particle X's wave function is A sub 0. Okay, I told you that. Which particle has a greater probability of being located at position X sub 0? Sorry, I said this is X sub 0. Right where it's sort of its biggest. Okay, that's not working out, but you'll just have to know. It's at its biggest. Which particle has a greater probability of being located at position X sub 0 at this instant and why? So this is a picture, really, right, because it can be graphed in position and time. This is a picture in time, okay, of where it is position-wise. So if you look at the four choices, the first choice is particle X has a greater probability of being located at x sub 0 because it spends more time passing through x sub 0 than the wave function of particle Y, right, which is a lot tighter. Or B, particle X, because the wave function of particle X is a longer wavelength than the wave function of particle Y, which is true. C, particle Y, because the wave function of particle Y is narrower than the wave function. That actually has nothing to do with anything. And part D, particle Y, because the wave function of particle Y has a greater amplitude near x sub 0 than the wave function of particle X. And the answer is D. And this is why, is that the absolute value of the wave function, okay, is related to the probability of finding the particle in some spatial region. But like I told you, think of it as a wave, right? So A cosine omega t or something like that. So the bigger, basically, the bigger the amplitude, the bigger the wave function. You can think about it this way. The bigger the amplitude, the bigger the wave function, the bigger the wave function, the bigger the probability. Oh my goodness, I don't know what just happened. The bigger the probability, okay? So really probability is based on the amplitude of the wave function done. That's it. And so obviously y is going to be a lot bigger, okay? Okay, we're going to totally shift gears and we're going to talk about how photons, light, can act like particles. It's a pretty weird idea. Sorry, I would pause it, but I have no idea how to pause this video. So you guys will just have to bear with me. Here we go. Okay, next topic is momentum and energy of a photon. Okay, so the idea is this is looking at photon or light as a particle. Well, why would you do that? Because there are experiments where you shine a light on something and it actually bounces off as if, just like it was like two ping pong balls, right? Or billiard balls or pool balls, right? If you had two pool balls, one hit another, and they would have a collision and they might go off at an angle, right? If you've never played pool, then try to find some time between now and tomorrow to go play so that you can just see what happens when balls collide with each other. So the cool thing is that they've shown some light at these these crystals, and knocked off an electron, and the photon deflected as well, just like it was a pool ball. So let me give you some formulas with it, and we're going to draw some pictures, and I actually have a Fizzlet that I'm going to try to play for you as well. Okay. Well, that's weird. How can I have momentum and energy if it doesn't have mass? Well, here's the deal. The relationship is this. This is the energy of a photon. And Einstein said we're going to relate it like this. It's going to be its momentum times the speed of light. Okay, so, well, we know that energy of a photon is hf, or E equals h lambda over c. Wrong, that's totally wrong, sorry. hc over lambda. Okay, so if you say that P equals E over C, right, just rearranging that, but we're going to take this. If you were to look at E over C, then E over C would be h over lambda, right? In other words, we can describe the momentum of a photon as h, Planck's constant, over the wavelength. That's a really, really important formula. You want to know that one. You want to know this one too. Okay? And you can actually check out the units if you were so inclined, and you would find out that they are the units of momentum, which are what? Well, they are kilograms meters per second. Okay, it's all true. Okay, so this is a proof. This guy named Compton. I can't remember. He was British, I'm pretty sure. I can't remember his full name. He scattered some X-rays against various materials. Oh, sorry, I keep yawning. he scattered some X-rays against various materials, and he discovered that the scattered X-rays had a lower frequency, which indicated a loss of energy. And he saw them do a few things, and he came up with some equations. So here's the deal. If you assume that you have an electron at rest, and you have a photon coming in, okay, so this is the incident photon. I didn't spell that right. Hopefully you can figure that out. Incident photon, that's the before story. The after story is that the electron takes this path. It's called the recoil electron. And then here is the scattered photon. And it is a theta below where it was. Obviously, you could flip this, right? Couldn't the photon come in, bounce off, and go up above? Sure. And I'm going to show you a fizzle in just a second. But let's go with this drawing, okay? So here's the deal. The photon loses energy. Why? Because it's got to give some of its energy to the electron. The electron was at rest. Now it's not. So that makes sense that the electron would gain some energy. And as a photon loses energy, that means that its frequency gets lower and its wavelength gets bigger. So there are a few equations going on here. First of all, the photon energy initially plus the photon, the energy of the electron initially, which was 0 because it's at rest, is the energy of the photon after the collision plus the energy of the electron after the collision. And that's going to just be kinetic energy, right? So we could look at photon like this. HF equals HF prime, where prime is after it, plus the kinetic energy of the electron. That's the electron after the collision. So that's something worth keeping an eye on. Okay. You can also say that this is true. HC lambda equals HC lambda prime plus KE of the electron afterwards. That's another way to do it. We tend to do the frequency, but worth keeping an eye on this equation as well. So he took that, and he took the fact of conservation momentum. So conservation of momentum says the momentum of the photon initially plus the momentum of the electron initially before, which, right, is 0, is going to be the momentum of the photon afterwards plus the momentum of the electron afterwards. That's just conservation momentum. And believe it or not, we do pay attention to the direction. We could break it into components and look at the conservation of the momentum in the x direction and in the y direction. That would be fine. But Compton did a whole bunch of work for us, and he derived an equation. Let me just give you one more fact about this one. So we can talk about h lambda equals h lambda prime. Again, these are the characteristics of the photon before and after, plus mv, right, of the electron. Okay, so Compton took all of this and combined it and made what's called the Compton equation, where he said lambda prime, that's the wavelength of the photon after the collision, minus lambda equals h over m sub e, that's the mass of the electron times c, all that times 1 minus cosine theta. Where did the theta come from? It came from that scattering angle of the photon. Okay, isn't that interesting? I never would have come up with that. Maybe you would have. Sometimes you'll see something called the Compton wavelength. And this is just equal to that constant, h over me times c. And it is a constant because, look, h is Planck's constant. That's obviously constant. Mass of the electron, that's constant. C, that's the speed of light, that's constant. If you put all those numbers together and you try not to round, what you get is 2.43 times 10 to the negative 12 meters. Okay, so mathematically, since cosine theta can only be between, hopefully you get this, -1 and 1, then that means that the range for lambda prime minus lambda, it can be as small as 0, in other words, not change at all, in other words, it doesn't hit the electron, right, it just goes right by it, up to and including 2 times the Compton wavelength. That is purely based on what the values for cosine theta can be, right? They can be from -1 to 1. Okay. So there's some problems that we're going to look at in just a second, but I just want to point out, first of all, once again, he proved that photon can act like a particle. We already knew that it could act like a wave because of Young's double slit, right? We saw the wave interference. And we've seen the electron act like a particle. Well, that's pretty easy. And we've seen the electron act like a wave. We talked a little bit about electron scattering and how it forms some interference patterns. So this is sort of the last piece of the puzzle. This is and the photoelectric effects showed this as well. So both of them showed that light can exhibit particle-like qualities. Some special cases you need to remember. Well, I guess just one special case, and that is that if the incident photon comes in and hits the electron, and then the incident photon comes back and the electron goes off like that. So one of the ways we can talk about this is we can talk about the photon momentum being in the opposite direction, in which case it would be negative. I think I'm going to do that for you in class because it's a little bit tricky, but that is the idea. Okay, I'm going to pause this video. I'm going to make another video with some practice. I want you to look at both videos. Let me just see if I can get this all figured out. Okay, wish me luck.